At 21 from chapter 17. This is proposing a problem. It says two students were giving benzoic acid, and asked to prepare benzaldehyde. So first you gotta know what benzoic acid is, hopefully we do. And it says the first student starts out by refluxing the sample of benzoic acid and thionyl chloride. So that is SOCl2. Upon completion, she evaporates the thionyl chloride to isolate A. So what does thionyl chloride turn a carboxylic acid into? That we should know. It's like activating an alcohol. So it turns the carboxylic acid into an acid chloride. Right? Remember, that was one of the ways we could turn a carboxylic acid, go up the mountain, right? Kind of sneak through the mountain. Then it says she treats compound A with stoichiometric amount of lithium triterbutoxy aluminum hydride, which is also known as dibol H. So this is a special fancy hydride source. The reason why it's fancy is because it stops at the aldehyde, right? Lithium aluminum hydride is so reactive, it'll keep reacting, right? More than one H will add. This one will stop, only add one H, and you end up with the aldehyde, which in this case is benzaldehyde. So dibol is a special reagent. I'll show you in class, probably Monday maybe. All right? So that gets you to benzaldehyde. The other route, the other student said, well, I'm going to take it. She took benzoic acid with excess lithium aluminum hydride. So that student used LAH. Now remember, we didn't talk about it specifically today, but I showed you what an amide would do or turn into with LAH, and it turns into an alcohol, where we add two H's. Right? Lithium aluminum hydride is a really strong H- source, reactive, so it reduces the carboxylic acid all the way down to the alcohol. And that's compound D in this case. Look at taking a ketone and reacting with multiple different things. So let's react it with HCN. Right? So HCN, right? You might have recognized this conjugate base, so it can be slightly acidic. All right. So that would have protonated the ketone, which of course makes the ketone more reactive. But it also generates this cyanide, which is a nucleophile. So then can attack, kick up, and you end up with this alcohol and a cyanide, or a nitrile now, oops, that has been added. Good? Just put that over there.
The alcohol group just staying on?
Yep, this is an OH. Alright, so let's keep trying something else. Same ketone. And let's react this ketone with LAH, lithium aluminum hydride, and then step 2, H+. So what's that going to do? What's lithium aluminum hydride going to do? It's going to be, right, so this is like an H- source, right? So it attacks, does the addition. O-, we added the H. So we've made a tetrahedral intermediate. We ask ourselves, are there any good leaving groups? Are there any good leaving groups there?
No.
No? So you're stuck. So you go to step 2. Step 2 involves H+. Let it grab H+. So you can turn a ketone into a secondary alcohol with LAH. You could also just use sodium borohydride, right? but this would work too. So you can turn a ketone with LAH into a secondary alcohol. So you can take that, we can shrink that guy up. Okay. Let's see what else we want to do with our portable ketone. Let's do our ketone, and it says trace acid, which is the same as catalytic acid. And we're going to react that with aniline. So anilin's what kind of amine?
Primary.
It's a primary amine. So we should be thinking what? Primary amine, we should be thinking
The amine.
imine, right? The imine. But the first step, of course, is going to be, right? We need to protonate, right? So activate that. Make our ketone more reactive. Now our amine can come back around and attack. We're going to need, so now we have a tetrahedral intermediate. If you have a tetrahedral intermediate, you ask yourselves, what's the best leaving group? The best leaving group here is the thing we just added, so that's no good. So we need to do
Proton transfer.
the old proton transfer. Alright, so we make water, which is a good leaving group. And we know we don't want to form any carbocations. So we have the lone pairs, or we even just have the O, the NH bond, those electrons there. Go. As we just generated an H plus, right? H plus. That H is this H, same H as this H. We've lost water, and we just made an imine. A circle like it has a double, it's a benzene ring there. So we just made the imine. So now we can grab that, shrink it up. Put you over here. Imine. Go by your buddies. There you go, shrunk that up. What else we have left to do? We got, let's see, we could do the ketone with H plus and a secondary alcohol, or secondary amine. So what's that going to do? Protonate. Good electrophile now. So now it can attack and add in the secondary amine can. So with the secondary amine, we should be thinking enamine in this case. Tetrahedral intermediate. What's the best leaving group? Thing we just added. You need to do a proton transfer. Right, so some of these start, the basic mechanism ideas for all of these doesn't really ever change. Like once you've seen one, you kind of hopefully you get the picture. Addition, tetrahedral intermediate, best leaving group, is there a leaving group? Elimination if it's possible, otherwise you're done. No carbocations. Alright, okay, tetrahedral intermediate now we have a good leaving group. We're not going to make a carbocation. Let's have the lone pairs come down, kick out the water. Now we're with something we actually call, I don't know if I named this, this is an aminium, because there's a plus charge in the nitrogen. We also generated some water. But why have a plus charge in the nitrogen when we could do a quick elimination here, and you could either use water to do this or just have the H fall off. Electrons go up. And now we can actually make our enamine. New pi bond. Nitrogen doesn't have a plus charge. But we've made H plus, which of course was our catalyst, so we know we're not done until we make the catalyst. And now we've made an enamine. Okay. Oh golly. Let's do one more.
2 more.
There's 2 more. Yep, one I haven't showed you yet, but I'll show it to you, why not? H plus and a diol. Alright. First step, by God, protonation. Made our carbon and the carbonyl more electrophilic. One of our alcohols attacks, it doesn't matter which one. We generate a tetrahedral intermediate. When we make a tetrahedral intermediate, what do we ask ourselves? What's the best leaving group? In this case, is the thing we just added. So, that's not good. We need to do a proton transfer. So we do a proton transfer. We turn this guy into water. But then the lone pairs come down and kick out the water.
Are you sick of this now?
Getting there. Let's shrink this. See where we're at now. And we just, right, no carbocation, so it's weird. There's a plus charge on the oxygen. Right? That's just because look at that as like another carbon on the carbonyl has been activated. Have the other oxygen attack, lone pairs. Make a tetrahedral intermediate, of course. Lone pairs go up. New oxygen bonded, the plus charge. Plus charge. We have a 2-carbon spacer. Tetrahedral intermediate, we ask ourselves, are there any good leaving groups, or do we want to do a leaving group? Kind of done now, I think. We don't want to take anything off we've added, right? I guess the way to think about it. So now we need to regenerate our catalyst, and we're done. And this is actually a really nice way to protect ketones and aldehydes, because they're not as reactive when they have this mask on. Literally, it looks like a mask, right? So not as reactive when they have the mask on. All right, shrinky dink time. Start moving some more things around, make some space. Got one left to do. Put these guys over there. Oh, no, don't overlap. Step 1, step 2 kind of. That kind of looks confusing. Shrink. 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 There you go. All right. One last guy. The old Wittig, which you haven't learned yet. But you're going to learn it now. Get excited. Basically, a Wittig reaction is a way to make alkenes. Turn a ketone or an aldehyde. Wittig. Wittig. This is German, like Wenzel, or Wittig, or Miller. Nope, that doesn't work. Kampf. No, doesn't work. Wenzel and Kampf and Wittig went to the Schnitzel. This is a recording. All right, continuing on. Wittig reactions allow for alkenes to be formed, and they do that with this phosphine reagent. So a carbon's bonded to phosphine, and the carbon rather had the negative charge than phosphorus. So carbon's technically more electronegative than phosphorus. It's close. We'll talk a little bit about how a Wittig reagent is formed later. So what happens is the carbon attacks, and at the same time, the lone pair, the pi bond attacks the phosphorus. So oxygen and phosphorus like being bonded together. PO bond. Al aluminum oxygen bond and phosphorus oxygen bonds are strong bonds. They want to be bonded together. Right? You guys already learned that, right? Remember PBr3 and PCl3? That oxygen want to be bonded to phosphorus? So what do we have now? We have this cyclobutane intermediate. So we formed a 4-member ring, and you guys could probably guess how stable do you think a 4-member ring is going to be?
No.
Not. And plus, I just told you phosphorus and oxygen like to be bonded together, right? So let's just move these electrons there and these electrons here. And what we've done then is we've formed a new pi bond, CC pi bond, and we've formed an oxygen, the pi bond to phosphorus. And of course phosphorus, because it's in the lower row of the periodic table, it can expand its octet. It doesn't need to have just 4 bonds, it can have 5 bonds. And these are our final 2 products. And this is called the Wittig reaction, a way to make alkenes from ketones and aldehydes. And that's the final one of this whole blowout scheme. Okay, so here's a good no, not quite fully retrosynthetic, but yeah, kind of. Saying you to start from here.
Oh, no. Nope.
That's the starting material. And we're actually going to make DEET, the bug repellent. So this molecule is DEET, which I used to work on in undergrad. The green synthesis of DEET using ionic liquids. So classic retrosynthetic problem, we got to work backwards. Right? If you look at this, just overall look at the problem, I would notice a couple things. Benzene rings in both places, a methyl is there, and this looks like so there's a bromine. Right? So you kind of look for where the action's at, where the polar bond's at. This looks like a polar bond, carbon bromine, and then this looks like a big functional group, right? So somehow I got to turn a bromine into an amide, and this amide. So that's the major goal, right? But I got to work backwards. So I got to think, how do I make amides? What's the easiest way to make an amide? Right? So then we go back to think about what? I would think about Mount Carbonyl. If I'm trying to make something as easily as possible, I'd rather start at the top and work my way down than try to climb up the mountain. So what's at the top of the mountain?
Want to be an halide? Halide.
Yep, acyl halide, right? Acid chloride, right? Or acyl halide. So instead of having a amine or an amide, I'm going to pretend that this was, before it was this, right? It was an acid chloride, right? Might as well go to the top of the mountain, right? Because even though I'm working backwards now, right? So it's like I want to be at the top as I go down, right? So now I want to actually go up if I'm working backwards. So I have an acid chloride. So where would an acid chloride have come from? How do you guys know how to make acid chloride? From what? So what was that called? What kind of functional group is that called? So if instead of having carboxylic acid, right? So we can make acid chlorides from carboxylic acids. Very good. How do I make a carboxylic acid? This one's a little tough. And if you hadn't been paying attention in the book, I didn't show this exact example. But we know we need to make a carbon-carbon bond, right? If you look back here, and this bromine, we make a carbon-carbon bond. So this carbon right now, is this carbon right here, if I label this carbon 1, so here's carbon 1 here. Carbon 1 right here, is it delta plus or delta minus, you think, when it's bonded to bromine? It's delta plus, okay? This carbon right here, if I label this carbon 2, the carbon of the carbonyl, is that also, what is that, delta plus or delta minus? It's not really delta plus, but it is delta plus. But it's certainly not delta minus, right? But that's a problem, because look, carbon 1 is bonded to carbon 2. And carbon 2 is delta plus. And in the beginning, carbon 1 was delta plus. So I got to make one of them delta minus. Do you guys know how to make a carbon of a carbonyl delta minus? No. But do you know how to turn a carbon that's bonded to bromine, make that delta minus? Anybody remember how to do that? How could you make something that was delta plus, delta minus? What if it was a Grignard? Right, you can turn a bromine into a Grignard by adding magnesium, can't you?
That's all.
That's all.
Add magnesium and that.
Absolutely.
Right.
Right, remember, if you have an alkyl halide with a bromine, if you add magnesium and ether, right, that magnesium jumps in between there, right? And all of a sudden, what was a delta plus carbon, right, delta plus now becomes delta minus, or full on minus, right? It's that Oompa chemistry, right? We make something that was delta plus now becomes delta minus. And now what piece do we need to add, what electrophile do we need to add in here, do you think?
Heat.
Nope.
Carbon dioxide.
CO2. You could add in CO2.
It's on the video.
Absolutely on the video. And then here, so now that goes back to there. So what do we need moving forward? Here we need magnesium, right? Because that jumps in there. We need to also add CO2 at some point. That'd be the next step, is adding CO2. So this is step 1. Step 2 is this. Right? When this attacks, the mechanism looks like, right? It attacks the carbon. Right? You make a tetrahedral intermediate. It's just weird because, right? You actually don't make a tetrahedral intermediate. I take that back. You're going to make this, right? O minus. So it's a carboxylate anion. And if you want to protonate that, what do you need to add? You need to add acid, H plus. That would give you the carboxylic acid. How do I turn a carboxylic acid into a acid chloride? SOCl2. And then if I want to take an acid chloride and make it into an amide, what do I need to add? The amine, right? But now be careful. How much amine do I need to add? You need to add 2 equivalences, right? Because you're going to make HCl. And if you make HCl, guess what the amine's going to react with? The HCl. So you need to add extra amine to make sure, right, you react all of it. Good.
Maybe it's from C.
Looking at this aldehyde. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6 over there. And it's saying H plus, and it's a catalyst. And they're asking what's the first intermediate going to be. So the first thing that's going to happen, we're going to protonate our aldehyde. Make it a better electrophile. Now this case is an intramolecular reaction. The amine is in the same molecule. Right, so the amine can attack to form a tetrahedral intermediate. And also forming a 6-membered ring and a plus charge, balancer charge on the nitrogen. So tetrahedral intermediate, we ask ourselves, what's our best leaving group? Still the amine, we just added that, so we need to do a proton transfer. All right, now we have a tetrahedral intermediate again. Bring our lone pairs down, kick out the water. You also should have noticed, what kind of amine did we start with? What kind of amine was that?
It's primary.
It's a primary amine. That means we should be thinking about making a imine. Imine. Right? And H plus is a catalyst, so the final step then is regenerating our catalyst. And that gives us this imine. Good. So now we have an imine. That was step one. Fancy, fancy, fancy. It doesn't need to be that small. Let's take that same imine, and now they're saying treat it with this NaBH3CN or H2 palladium and see what happens. So NaBH3CN is just a fancy sodium borohydride reagent. It's still an H minus and it's still BH, right? So what do you think is going to happen? If this is an H minus, what do you think is going to happen? It's going to attack the amine, right? We'll make a tetrahedral intermediate. And then we usually need to work up with an acid. There has to be some H plus around. They should have put that on there. And you end up with the amine. Now, if you had used the H2 palladium on carbon, right, that would be a different mechanism, right? That's the palladium adding two H's at once. But this is, gets you to the same place, get the amine. So you can turn an imine into an amine with NaBH4, this fancy kind of sodium borocyanohydrin. Same idea though, same mechanism, just a little different. Right, we're gonna start out with an alkene. We don't know what it's gonna turn into, or we don't know what reagents we need, but we're gonna make it into this imine. So, we gotta do a retrosynthetic analysis, because that's what you do. Because it's gonna take more steps than reasonably you can move forward with. So we have an imine. What is an imine? What does an imine come from? A primary what? Primary nitrogen, so amine. And what else? In this case, it's going to be what? Ring with a what kind of
No, with
aldehyde, right? With an aldehyde, right? I didn't draw the H in, but it's there. And they don't either, so it's an aldehyde. Okay, so I think we can leave the amine part to the side now, since, right, looking at this, right, there's a pi bond here, there ends up being some stuff out here, so obviously we're turning this pi bond, this alkene, into this imine somehow. So we already got to this point where we have an aldehyde. Cool. Working backwards. What do we make aldehydes from? How do you guys know, how many ways do you know how to make aldehydes? Where do aldehydes come from? An alcohol. What kind of alcohol, Blake? Calling you out on here. Primary alcohol. Such conviction in your voice when you said that. Primary? Primary? Alright, we have a primary alcohol. So it's an alcohol that's on the less substituted carbon. We call that the anti-Markovnikov product. Can we take this alkene, moving forward, and put the alcohol on the less substituted carbon? What is that? What reagents are those?
That's like last exam. I don't
It was more than last exam, it was like last year. If I want to turn to anti-Markovnikov, remember that's that BH3? It would be step 1, and then they separate out as step 2 is NaOH, H2O2. So that BH3, step 1 and 2. That gives us the anti-Markovnikov product, right, from the alkene. Right, if we number our carbons, 1 and 2, 1 and 2, 1 and 2, 1 and 2. What reagents do we use to turn a primary alcohol into an aldehyde? You have two options.
You could do PCC
PCC is one.
or chromium in quotation marks.
Nope, chromium would take it all the way to the carboxylic acid. Chromium is too strong. It's the NaOCl, the bleach. So it's PCC or bleach would do it. Takes 1H. And then if we want to make an imine, is an aldehyde reactive enough to react with the amine? Or else we need to make that aldehyde more reactive.
Acid.
You need some acid. That's right. You need some acid. And there you go.